Hi, my name is Alex Schaefer, and I am the coding specialist.
My name is Jack Wooten, and I'm the materials design specialist.
My name is Casey Maduka, and I'm the lead coder.
My name is ZJ Wei, and I'm the coding specialist.
And we are Team C.
An advanced energy vehicle was necessary for the transportation of R2-D2 units for the Rebel Alliance, which was rebuilding their army. They wished to utilize an AEV as it was both efficient and cheap. The AEV transport system must be consistent and focus on conserving as much energy while meeting all of the constraints and guidelines. Team C's overall goal was to develop an AEV that can perform the scenario effectively. The team designed, tested, and implemented an AEV to showcase to the Rebel Alliance, also known as the instructional staff.
The team started with a sample AEV design to build a foundation for future design iterations. Each group member then made their own individual design based on what they thought would make the most efficient vehicle. The team then came together to make one group design based on the best aspects of each individual design created.
When the team was initially deciding what to do for the code, we thought we want the most efficient AEV possible. And for this to occur, we need to know several factors that went into how the AEV moved and operated on the track. We decided to use stuff that we learned from physics, including stopping distance and acceleration and velocity and friction, and we learned that we could effectively capture the best moment to stop the AEV's motors. For the AEV run to be considered successful, the code had to guide the AEV along the track and trigger the gate's first sensor without hitting the second. Then it would wait for 7 seconds until the gate lowered before proceeding. Once the gate was lowered, the AEV was to travel to pick up the R2-D2 unit with its front magnet. The AEV then traveled back to the gate where it stopped before continuing. After passing the gate successfully another time, the AEV guided the R2-D2 unit back to the start of the track.
One advantage our group had compared to other groups was the resiliency to different environments and conditions. When testing on different tracks, the AEV was able to adjust accordingly and stop at the same location without any modifications to the code. Even when the AEV lost a propeller during the run, it was able to detect when it was traveling slower and stop at the correct locations.
Among the several troubleshooting techniques that the team utilized, the flashing LEDs really helped determine what the AEV was doing during its track run. For example, when it was slowing down, the colors in the AEV turned blue. When it was speeding up, the colors turned red, and when it stopped at a gate and started flashing, that meant that the AEV was waiting until the gate opened. Finally, when the AEV finished its run, the lights would turn green.
This success did not come without its difficulties. Typically, the AEV would overshoot the target mark or neglect to turn off the motors in time. The code that was developed helped minimize the number of such errors by allowing swift changes that could quickly be tested. The creation of animated charts and data overlays that were placed on top of video recordings of each run helped pinpoint the exact moment when the program did not act as expected, reducing the amount of time spent debugging.
After the team successfully completed the mission and final testing, our goal of creating a lightweight, energy-efficient vehicle was fully implemented. Through the multi-stage design phase and the testing of many unique configuration ideas, the team was able to create a great final design.
Overall, we are very happy with the final design, given the constraints and problems the group faced.